All right, so in section 5.1, we were talking about mathematical induction, which is sort of an application of the idea of recursion to proofs. But what we're going to do in section 5.3 is look at recursion when applied to like defining sets or sequences, that sort of thing. So these are called recursive structures. Something inherent to the structure of the set is recursive. And so we're going to start with a sequence. Here's a sequence written out with the notation I like to use for lists, which is that square bracket notation. Another way to write out a sequence is using braces like a set, except giving each element an index. So you sometimes see it written like this: braces with an is equal to, and then braces, we write a1, comma, a2, comma, a3, and so on. So with that notion, with that idea of using an index, a subscript, it gives us a way of associating each element in the sequence with a positive integer. So we can imagine that the number 1 is mapping to the first element of the sequence. 2 maps to the second, 3 maps to the third, and so on down the line. So the first thing I want to do, and this is not really related to recursion at all, but just related to sequences in general. First thing I want to do is describe to you how we can define a sequence as a function. So what we have here are, these are like our inputs. The red positive integers are inputs, and the outputs of the function are, well, whatever set contains the terms in the sequence. So in this case, this is an integer sequence. There are both positive, negative integers and 0 in this sequence. So we will use as our output the entire set of integers. But you could just as easily make like a sequence of real numbers, something like that. The output could be anything. Oh, you could make a sequence of sets, whatever. But the input is always the positive integers, because first element, second element, third element, and so on. The input of the function are the values of the index. All right, so we can write f maps from z plus to z, and we can start writing down what the terms in the sequence are by stating them as like function results. So we can write f of 1 equals 1, and f of 2 equals 1 as well. F of 3 equals 0, and so on down the line here. All right. Okay. So now what we're going to do is we're going to write a recursive definition of this sequence. We've got to figure it out first. And we're going to write it in the language of F. We're going to use the function notation to define our sequence here. There we go. The way that I've started writing down the function so far is not a very good way to define it, because if this is a sequence that's going to go on forever, if this goes on, to infinity here, it's an infinite sequence, then I can't just list all the elements. That's impossible. So instead, we have to find a pattern, right? I can get up to the 10th element in the list here. So I will get up to f of 10 equals 13. But then what is f of 11, right? To determine that, we need to identify what the pattern is in the sequence and then express that pattern somehow. Now, some sequences have what's called an explicit formula, or like an explicit definition, where you can write a function like f of n equals blank, and it's just a formula that spits out the nth term in the sequence. That would be great. Not all sequences lend themselves to that sort of description. So we're not going to do that. That's an explicit description. Instead, we're going to do a recursive description, where you say what the next term in the sequence is in some way, like in terms of the previous terms. All right, so a great example of this, probably the most famous example of this, is the Fibonacci numbers, where to get each term in the sequence, you add the two previous terms together. That is a recursion rule, right? It relies on the most recent numbers that you've just seen, right, to get the next one. So you've probably all seen the Fibonacci numbers. I'm not going to go over what those are, but having brought that up, you may notice that the numbers you're seeing in this sequence resemble the Fibonacci numbers. Fibonacci numbers are 1, 1, 2, 3, 5, 8, 13, and so on. So these numbers are actually the same as the Fibonacci numbers, except that their signs are alternating back and forth. And something weird is going on over here. Maybe weird, maybe not. So let's see if we can figure out how this is different from the Fibonacci numbers. Similar, but not the same. I'm going to pause. I want you to pause the video and take a second to see if you can figure it out. And then I'm going to go ahead and say what the answer is. This takes a little bit of experimentation to try to see if you can identify how the terms are related to each other, what the sort of pattern is. Are you adding things together to get the next term, or is it like multiplying or something like that? There's a lot of different kinds of patterns that you can make, but this one's pretty straightforward. So I'm going to say what it is now. The pattern we're seeing here is that terms in the sequence are subtracted to get the next term. So let's look at an example. -3, if you do -3 minus 5, you get -8. So right there, we see that is the pattern. This term minus this term equals this term. We can see it. Let's do it again, one step further down. 5 minus -8 equals 5 plus 8, which is 13. So there's another example of the pattern. And you can keep on doing that pattern. So -8 minus 13 would be -21. So the next number is going to be -21. F of 11 will be -21. And so on. Okay. Now we can check back at the beginning of the sequence as well. It still works down there. You can check it here. 1 minus 1 is 0. 1 minus 0 is 1. 0 minus 1 is -1. 1 minus -1 is +2. So okay, so we've identified the pattern, and basically that was done by just sort of exploring the numbers and finding the pattern. There's lots of sort of different approaches to that, but it's a bit of a trial and error sort of approach. That pattern there is the recursion rule. So now we get to finally write our definition. So there's two parts to a definition. There's the base case or cases, depending on the situation. And there's the recursion rule. The recursion rule is sort of like the equivalent of the inductive step from mathematical induction proofs. So we've just found what the recursion rule is, and I want to write it down in terms of the function. It's that f of n is going to be the two previous numbers, one minus the other. So -8 was -3 minus 5, right? So that would be, or let's do another one back here, actually. Let's do 2 was equal to 1 minus -1, right? So that was the fourth term minus the fifth term gives us the sixth term. So the way I can write it is the nth term is going to be the n minus second term. Like you have to go back two steps, and then subtract the n minus first term, which is just back one step. So this is f of n minus 2 minus f of n minus 1 equals f of n. All right, so that's our recursion rule. Now, because our recursion rule relies on two previous terms, in order to get started, we have to give the function two terms to work with. So in this case, for our base case, we actually need to state f of 1 equals 1, and we need to state f of 2 equals 1. Once you have two terms in a row, then you can apply the recursion rule. With only one of those terms, there's just not enough information to apply the recursion rule. It relies on two. So there we go. So that is an example of a recursive definition. Both of these parts together form the recursive definition of that sequence.